Hello everyone, welcome to a fresh new lecture on the topic Introduction to Time Frequency Analysis. This is Dr. Anirban Dasgupta and let's get started. So, we have already covered two modules, first on time domain signal processing and the second on frequency domain signal processing. And what have we learned? So, we can represent a signal something like a sinusoid in time domain, and in time domain we see how the signal amplitude varies with time, and from this we can estimate or compute the frequency of the signal or of the sinusoid, and that is in 1 second we see that there are kind of 50 complete oscillations. So, I can say the frequency of this signal is 50 hertz. The second modality is analysis in the frequency domain. So, here we see that it has a frequency at plus 50 and minus 50 hertz. So, both the domains give kind of an idea that what is the signal about. Of course, there can be a shift in phase. So, just the amplitude or the magnitude spectra will not tell about that information. So, you also need the phase spectra, but related to the frequency content we can understand that what is the signal all about. And again, since this is a windowed version of the signal, this is just a part of the signal. So, we do not get exactly one delta or one impulse at plus 50 and minus 50, but rather we get, you can see it is not very much distinguishable, but there is a finite spread because of this windowing effect. Now, then what is the problem? This looks very nice. So, again if we have a sum of sinusoids, for example, say we have a signal which is a sum of 10 hertz, 20 hertz, 30 hertz, 40 hertz and 50 hertz. In time domain we can see this signal is like this. Now, of course, just looking at the time domain signal, it is really difficult to say that this is composed of these 5 frequencies. But if we see the frequency content in the spectra, so we can see that all the 5 components are present, which are 10, 20, 30, 40 and 50. So, what is the problem again? What about this signal? Now, this is a very interesting case. So, here in the first second I have a signal, a sinusoidal signal which is of 10 hertz, because we can see 10 complete oscillations, and in the second we have 20 oscillations, or we can say up to 0, from 0 to 1 hertz the frequency is 10 hertz, from 1 to 2 hertz the frequency is 20 hertz, from 2 to 3 the frequency is 30 hertz. Now, you can calculate and count and you will know that it is 30 hertz. From 3 to 4 seconds the frequency is 40 hertz, and from 4 to 5 the frequency is 50 hertz. And what about the spectra? Well, the spectra looks very much similar to the waveform in the previous slide, like this. Of course, because of this windowing effect you see a lot of leakage, because this window is short for each 10 and 20 and all the frequencies, they exist only for 1 second. So, we get a larger spectral leakage, whereas here the window is of course for 1 second, but this is combined for each. So, the leakage found here seems to be less. But what is the problem? The problem is that in the frequency analysis we are able to detect all the frequencies present in the time domain signal, but we do not know where that frequency is present. Like the frequencies can be a combination, a superposed version of all the sinusoids, or each sinusoid is occurring separately, but at different time durations. So, this is a critical problem. Let us look at another problem. So, here we see that we have a sinusoid which is of how many 10 hertz, and this is what we observe except for the period 2 to 3 hertz, where we have a sine of 10 hertz multiplied or say added with another sine with 50 hertz. So, if we see the spectra, we see that the 10 hertz component is dominant because that is appearing throughout. However, we also get components at the 50 hertz location. So, we know that there is some 50 hertz present in the signal, and mostly it is a 10 hertz sinusoid. But where this is present, that information is not available in the frequency spectra. But if you see the time domain signal, we know that the signal is oscillating at 10 hertz except the interval 2 to 3 hertz. So, in this duration we know that this is not just a 10 hertz signal, there is something more to this 10 hertz signal, but we do not know what frequencies are there. So, frequency spectra is telling me that what frequencies are there, but where is it there, I do not know. But the time domain is telling me that there are some spectra, and where it is I can understand, but what frequencies I do not know. So, just knowing one version of the signal may not be sufficient to get the clearer picture of the holistic thing, and this is often what happens in real world. So, real signals are not purely sinusoid throughout. There can be somewhere where the high frequencies are there, in some places there may be low frequencies. So, if we just see the time, we can see that where my faster oscillations are there and where slower oscillations are there, but we cannot exactly determine the frequency just by looking at the waveform. Whereas, in the frequency spectra or frequency domain, we can locate what frequencies are there, but where it is there we do not know. So, that brings the concept of time frequency analysis. So, what is time frequency analysis? So, this is concerned with simultaneous analysis of signals in time and frequency domains. Like if you see this signal, so here I can see the signal in time, that how the signal is behaving, and also, but I do not know what frequencies are present in this signal. But I can say that okay, in the early stages of the signal has a very slow change with some kind of noise, and in the middle stage there are a lot of fluctuations, that I can say in time, but what frequencies are there I do not know. Whereas, in the frequency domain, by seeing the energy spectral density, we know that these are the dominant frequencies, but where these dominant frequencies are occurring we do not know. So, if we look at this kind of representation, which is called a time frequency representation, often this is also called a spectrogram. So, here we can see that at these time instance which frequencies are dominant, and at this time instance which frequencies are dominant. So, this two dimensional representation gives how the signal is behaving with respect to both time and frequency, and the color map is giving the amplitude of that specific frequency at a specified window in time. Why I say window, that will be clear soon. So, this is a way to represent a signal in both time and frequency simultaneously, and this plot is often called a time frequency representation TFR or time frequency distribution TFD. So, this is another real example of an EEG signal, and this kind of physiological signals like EEG, ECG, these are even speech widely use this time frequency representation, because here the practical challenges come that I want to not only see the frequencies, but where those frequencies are present. So, again here if you see in time, we see that here the oscillations are faster, here maybe they are slightly slower, and in the frequency we see that near 10 you have a dominant oscillation or dominant frequency, but this dominant frequency throughout the signal. So, So, if you see the spectrogram or the time frequency representation, so here you can see that, so this red markings are showing that the intensity is high of that frequency. So, this location and this location, this 10 hertz frequency is very much dominant, whereas in this location this frequency is absent, because you get a blue line which means low amplitude, and in these locations these lower frequencies are present which is below 5 hertz. Okay. So, why do we need time frequency analysis? So, one thing I have already explained, but let us still try to understand. So, non-stationary signal analysis. Now, in time domain signal classification, we discussed that signals can be deterministic or stochastic, and in stochastic signals, signals can be stationary or non-stationary. Stationary means that if I move throughout the signal properties like mean, variance and your distribution or your spectra will not change, while in non-stationary signals at different instances of time these characteristics will change over time. Like speech signals for example, so different phonemes have different frequency patterns and these patterns occur at different times. So, joint time frequency representation helps us see both the things, that which frequencies are present and where they are present. So, these two together help us get a very good idea that if a frequency is present in the signal, it does not mean that it is present throughout the signal in the time domain. It may be occurring in specific regions in time, and that brings to the concept of localized events. Like say if I am observing a seismic signal and then there is a sudden vibration. So, that duration when there is a say like this and suddenly this and this. So, this is a high frequency oscillation and this is not present throughout, this is present as in a specific window in time. So, if I can get this information that this frequency content is in which area in time, that is an event, that is marking of an event. Similarly, say when I am recording the EEG signal and say I am moving my eyes like this, so there is a specific frequency content present at that location. So, I want to capture that specific region in time where those specific frequencies representing the eye movements are present. And also improving signal processing, like if I know that region, that is an artifact in the signal, so I can easily filter them out or remove them. Also, if I want to have some idea of noise, so denoising reconstruction will be very useful by doing a time frequency analysis. So, these are applicable in areas like communication, radar and biomedical signal processing. And the tasks are filtering and denoising, they are kind of same, and this helps us better analyze and improve signal processing. So, now we have a good introduction to what is time frequency analysis. Let us understand what are the popular time frequency analysis method. So, the first is short term Fourier transform. So, what is short term Fourier transform? As the name suggests, so it is a Fourier transform which gives me frequency, but it is a short time, like I will not do the Fourier transform of the whole signal together. I will take small windows, do the Fourier analysis, another window Fourier analysis, and in this manner I can get the spectra of each window. But typically this window size is kept same in short time Fourier transform. What about wavelet transform? Wavelet transform extends this idea to non-sinusoidal basis, like if I have a signal which has a sharp change like this. So, probably if I use sinusoid, it might not be very convenient and it may take a lot of coefficients or lot of components to approximate this signal. But rather if I analyze this kind of signal with a sharp kind of a small module or basic signal which I call wavelet, then this will be easier and faster to analyze. Then Wigner-Ville distribution is kind of similar to short term Fourier transform, but it has a smoother representation and it does not follow fixed window limitation like STFT. And then finally, we have the Hilbert-Huang transform HHT, which is also popularly known as empirical mode decomposition. Now, empirical mode decomposition, one may argue that it is a purely time domain analysis technique, and the concept of frequency, although it is not present, but Hilbert-Huang transform, what it does is it decomposes any signal into two modes. One is an oscillatory mode and one is a trend. So, trend means if the signal is having some component which is going up or going down, that is a linear trend. The trend may not be linear, but this is the non-oscillatory component of the signal. And then the oscillatory components can be components which are varying slowly, that is you can say it is a band of frequencies, but the frequency term is not used in HHT, or it can be very fast moving components, and these are called IMFs, intrinsic mode functions. So, if we see an example of time frequency representation, one of the best example is to see the chirp signal. Now, where do we hear the word chirp? So, in the morning often we hear the birds are chirping. So, what is so special about a chirp? So, chirp is a signal where the frequency slowly increases or decreases with time, and there are linear chirp where the frequency increases or decreases linearly with time, and this is an example of a linear chirp, and this is the spectra of a chirp. And from this it is very difficult to identify that this is composed of not only these many frequencies, but these frequencies are happening separately at different time locations, like this is a high frequency region and this is a low frequency region. So, in this kind of signals, time frequency analysis is very useful, because with just time domain I do not know what are the frequencies, and in frequency domain I do not know where it is occurring, because this is kind of a flat spectra which is denoting there is an impulse kind of a thing, but actually it is something totally entirely different. So, in time frequency representation in spectrogram, which is typically used in STFT, so this is what we are getting. So, here the frequency axis is given in a like logarithmic scale, and this is the time axis. So, here we see that if we see around 2 seconds, so this is the frequency content which is low, and as my time is increasing, my frequency component is going on increasing. See, the yellow color is giving you the highest magnitude, that means this is the dominant frequency, and this dominant frequency is increasing with time. So, here we get a very nice representation that what frequencies are present and where they are present. And to explain the graph, so say the chirp signal for example, so this is a frequency modulated signal, that is the frequency increases or decreases over time. Here it is increasing, and the frequency starts at 10 hertz. If we see, let us see here, so this is starting at 10 hertz. I have programmed that in that way, and it increases up to 200 hertz, and that is unfortunately pretty difficult to see because it is looking all continuous here, and it is spanning over 5 seconds, that is this. So, if we plug in this general value, so this is the general equation of a linear chirp signal. So, A sin twice pi f naught t, f naught is the starting frequency which is 10 hertz, and then plus f1 minus f naught by 2t, where f1 is the ending frequency 200 hertz, f naught is the starting frequency 10 hertz, and 2t, t is my duration which is 10 seconds, and this t and this t square is giving me the instantaneous time t and t square. So, this plugging the values we get this relation, and that I have plotted in the time domain. So, this type of signals is commonly used in radar and communication systems to observe how frequencies change over time. So, in this spectrogram we see that the time frequency plot is generated and the colors are based on the magnitude of the Fourier coefficients for each time segment and frequency. We have also given the color bar. If you can see, this is the color bar, and this yellow region shows that the high value of frequency amount or magnitude, and black means low value, which means in these regions the frequencies are not present. So, if you take just a section, that is the Fourier series or Fourier transform of that specific window. And we have used a logarithmic scale, because linear scale it will be harder to see, because the frequency is increasing very fast, like we have 10 square and 10 cube. So, in a logarithmic scale 10, 10 square, 10 cube will be equally spaced. So, we see that this STFT provides a dynamic view that how the frequency contents are changing over time, unlike our simple Fourier transform that will give a single spectra that what frequencies are present. So, what are the challenges in time frequency analysis? The first is the time frequency trade off. Now, what does it mean? So, for example, if I draw a complete sine wave, and if this is my time t, then I can know the frequency is 1 by t. At least if I draw half it, still I am able to know that this is what frequency. But if I draw 1/4 of the wave, it is probably that frequency, but it may also increase. So, if I localize in time very small, like if this is my curve, what does it mean? I do not know. It may mean a high frequency or low frequency, it is very difficult to say. And if I just give a dot, like at a specific instant, if I say that at t equals to t naught, tell me what frequencies are there, can I tell this point can be representing any frequencies? So, if I localize in time very accurately that at this exact moment, then I am very much uncertain about what frequencies are there. This is looking like an impulse, everything is there. And the higher I visit, because this is again a sine multiplied by a rectangular window, the more cycles I plot of the sine, the better, like this will have a frequency at something like 1 by t, but the more cycles I plot, the narrower will be the spectra. And if I go with infinite cycle, then I get a precise spectra at that point. So, the question is that if I localize too much in time, I do not get the exact frequency, I am very much uncertain about frequency. But if I increase the time plot, I am very much certain about the frequency, but then I am uncertain in time, because in time I am getting a wider window, right. So, if I am very much precise in frequency that exactly tell me 50 hertz is present, then I have to go the entire time from minus infinity to infinity. And if I want to say that okay, at t equals to 5 seconds, what is the frequency? I do not know, I am absolutely clueless. So, there is a trade off between time and frequency, like if I say there is a delta t time, I am observing the signal. So, in this delta t time, tell me what are the frequencies delta f present in the signal, and if this delta t will decrease, the uncertainty in delta f will increase, and similarly if the certainty in frequency will increase, the uncertainty in time will decrease, and vice versa. So, that is the uncertainty principle, which makes the selection of window size very critical, because what is a good window, so that I get an optimal resolution in time and frequency. Another is complexity, because calculating 1D vectors in time domain or frequency domain is easier than computing matrices or dealing with matrices, and this will give high dimensional data, the spectrograms. So, hence this is a real challenge, and people are still working on this, because in real time applications like radar and telecommunication or even medical signal processing, this is a critical challenge in using time frequency analysis methods. Also noise. Now, already noise is a challenge, be it time domain or frequency domain analysis. And in time frequency, because you are taking windowed, you sometimes may not be sure that whether a specific pattern is because of noise or because of a signal component, and that makes filtering and denoising extremely difficult and complex. So, to start with these challenges, one of the basic is to use adaptive resolution. And what is adaptive resolution? Like seeing the signal at different rates, and that is the concept of multi-rate signal processing. So, here the signal can be downsampled for analyzing low frequencies and upsampled when focusing on high frequencies. So, this method is the fundamental basis for studying the wavelet transforms, and with using multi-rate or multi-resolution, sometimes it is called in case of images, this helps to analyze the signal very nicely. So, hence we will understand what is multi-rate signal processing in our next topic. Thank you so much. Have a nice day.